So we made this dot plot yesterday, and we said that each one of these dots represented one random sample of M&Ms and another random sample of Skittles, and the difference of proportions calculated from those samples. If you squint at it, so it's a little bit fuzzy, how would you describe the shape? I would say approximately normal. We've got a big bump of data right here in the center. We got a little tail off to the left, and we've got a tail off to the right. So I would describe this as approximately normal. Looking at that graph, if I asked you to eyeball what you think the center is, the mean, would be about what? Negative 0. What? Negative 0.1, so about here. Does that look like about the center to you guys? I'm fine with that. Negative 0.1. I think it's 0.01. Let me go check the scale again. Yeah, because negative 0.1 is right here. So this would be negative 0.01 right here. All right, and now I'm going to ask you guys to do something a little bit different. I want to try to figure out the variation, approximately. What do we use to calculate variation or to talk about variation usually? Standard deviation. Do you guys remember back when we first learned about a normal curve? And we talked about something called the empirical rule, the 68, 95, 99.7 rule. Does that sound familiar? 68 was one standard deviation away from the mean on both sides, and it had to capture 68% of all the data. So if I'm looking at this, if I wanted to like ballpark the standard deviation, I want to look at how far out from our center, we said our center was about here, about how far out on either side would I want to go to capture 68% of all of those dots. So from here, how far out do you think you would want to go on either side to catch 68%? And let me draw where we said our center was approximately. We said the center was about here. This is the approximate mean of negative 0.01. How far out would you go on this side? If you wanted to capture most of the dots. 0.04, so like cut it off here-ish. What about on the other side? If I go that same distance on the other side, let's see, that'd be to right here. Do you think that captures about 68% of all of the dots there? So to go from here, negative 0.01, did I go out far enough on the other side? Yeah. Over to here. How far is that? Yeah, 0.05, 0.06, somewhere in there. Again, I'm just kind of eyeballing this. So about 0.0, let's pick one. Do you want to go with 0.05 or 0.06? 0.05, sounds good. If you look down at the very bottom of the page next to the stop sign, there is a line of text that was supposed to print at the top of the next page, but I messed up. Can I get somebody willing to read the text down by the stop sign at the very bottom of the page? You'll read it for me? Awesome. What's it say?
Google reveals that 25% of M&M's New Jersey factory are orange and 20% of Skittles are orange.
Awesome. All right, so we're going to turn the page. We know that the true proportion of orange candies for M&Ms, they said was what, 0.25? And the true proportion of orange Skittles, according to the factory, is 0.20. I want to know the shape for each of these. So we're going to do these one at a time, one sample each. What do we do to determine the approximate shape? Large counts. I would like for you guys to check large counts for M&Ms and then come over and check large counts for Skittles. What was our sample size again? Sample size was 50. Look at the front side again. I believe our sample size was 50. Thank you, dear. So sample size of 50. I want you guys to calculate large counts for M&Ms and large counts for Skittles. We're on the next page. But at the very top, so you barely missed anything. Do we get large counts for M&Ms? Yeah, what is n times p? 12.5, and we need it to be 10 or larger. We got 10 or more. What is n times 1 minus p? 37.5. That's 10 or larger, which means this is shaped approximately normally. Do we get large counts for Skittles? What is n times p there? 10 exactly. N times 1 minus p? 40. And so this would also be approximately normal. Perfect. How do we calculate the mean for p hat? Yep, it is whatever p is, whatever the true probability is. So what's the mean for my M&Ms? 0.25. Mean for Skittles? 0.20. How do we calculate the standard deviation for p hat? Square root of, yep, p times 1 minus p over n. All of that underneath the square root. So the square root of the fraction, p times 1 minus p over n. I would like you guys to calculate the standard deviation for both M&Ms and for Skittles. What is the standard deviation for M&Ms? 0.0612. Yep, we have to do P1 times 1 minus P1 over N1. So we do 0.25 times 0.75 over 50, all underneath the square root. You should get 0.0612, about. What about for Skittles? What's our standard deviation there? How much? 0.057, yes. Or 0.0566, depending on exactly how you rounded it. So far, so good? All right. So these are both random variables. Do you guys remember doing random variables last chapter? We have random variable for M&Ms. We're going to call that random variable X. It is distributed approximately normally. We know the mean. We know the standard deviation. We have our random variable for Skittles. We're going to call that random variable Y. It is distributed approximately normally. We know our mean. We know our standard deviation. Do you guys remember when we combined random variables? When we put random variables together? If I want to add two random variables, what do I do with their means? You add them. If you want to subtract two random variables, what do you do with their means? You subtract them. What about standard deviation? You add the variances and then you square root it. You add the variances and then you square root it. So let's look at what happens when we put these two random variables together. So for a two-sample situation, how did we say the M&Ms were distributed? Approximately normally. Skittles? Approximately normally. So how do you think the difference will be distributed? Approximately normally. When I'm trying to determine the shape for a difference, subtraction, of two random variables, I have to check large counts for both samples. You have to check large counts for population 1. You have to check large counts for population 2. You guys already told me that we're going to subtract the means. So the mean of the difference would be 0.05. Mean of p hat 1 minus p hat 2 is going to be p1 minus p2. It's always standard deviations, though, that are a little bit weird. Because we don't add standard deviations, we don't subtract standard deviations. We always add the variances and then square root. So to find the standard deviation for this difference, I need to take the standard deviation of each of those individually, square them, and add them together. I would like for you guys to calculate that. What'd you guys get for the standard deviation? 0.0834. In formula form, this is what that looks like. This first part is the variance for my first sample. The second part is the variance for my second sample. We add those variances and then we square root. Do I expect you to memorize those formulas? No, please don't waste your time. Learn other things instead. I'd rather you remember other things. I want you to know where to find them on the formula sheet. I want you to know how to use them, but you don't have to memorize these formulas. So we talked the other day about where on your formula sheet you can find these. This is on the back of the front page in the box up at the top. It's labeled sampling distributions for proportions, which is what we're looking at right now. In the very top row, it's for one sample. And then this box down below it that has a whole bunch more junk in there, that's for two samples, for two populations, which is what we're doing right here. Standard deviation formula is right here. I would like for you guys to do question number 7. We now know the distribution. We know the mean. We know the standard deviation. I would like for you to calculate the probability of getting a difference in proportions of a positive 0.08 or higher purely by chance. What do you need to start with? Draw a picture. We already did our 10%. We checked that one already. Yes. We checked 10% condition already. We don't have to do that one. If we hadn't already checked 10% condition, then we would need to. But we already got away with that. So draw your picture. We said it was approximately normally distributed, so you need to draw a normal distribution. You're going to need a graphing calculator or the app so that you can do your normal CDF. Yes. Yes. Not down there. It's just the positive one. That's a good question. Guys, please pay attention to the fact the difference in proportions is a positive 0.08, not plus or minus, just the positive 0.08. If it just said a difference of 0.08, then we would look at the plus and minus. But in this case, they told us specifically just the positive one. Thank you so much. So your picture should look something like this. Double check your picture against mine. Your probability notation. We want to know the probability that p hat 1 minus p hat 2 is greater than or equal to 0.08. Probability that p hat 1 minus p hat 2 is greater than or equal to 0.08. And so we're going to use our normal CDF to do that. Lower bound of 0.08, upper bound of something enormous. Mean of 0.05, standard deviation of 0.0834. And you come up with a probability of about what? Yes, I got 0.3595. So this is the probability that the difference in my sample proportions. Yes.
So when would it be regular P?
I'll have to wait until I see an example and then I can point it out. Like, I'm just blanking on exactly what that would look like. Let's go ahead and take this over to page 15. Page 15, some big ideas. So a sampling distribution of a difference, sampling distribution of p hat 1 minus p hat 2. The shape will be approximately normal if and only if we pass large counts for both of our samples. The center will be P1 minus P2. The variability, the standard deviation, you have to check the 10% condition for both of these groups individually. Check 10% condition for POP1, check 10% condition for POP2. If they both pass the 10% condition, then you can use this formula for calculating standard deviation. I want to give you guys about 5 minutes to do the check your understanding. And as a reminder, they will never tell you check your large counts. They will never tell you check your 10%. You need to know when you should do that and why. So take 5 minutes to work on this. What do you need to do to determine the shape? What do you need to do to find the mean? What do you need to do to find the standard deviation? So n is 30, because remember, little n is your sample size, so that would be 30 times 0.65.
Oh, okay.
Yep. Nice catch. Hey, do you need any help? Are you okay? Okay. What is the shape of the sampling distribution of p hat s minus p hat j? Approximately normal. Why? Because large counts. So when we did n times p for the seniors, what did you get? What was our sample size? 30 is our sample size. That's n times p. So we need to do 30 times 0.65. 30 times 0.65 would give us 19.5. So we still pass. We still have 10 or more. And then we do n times 1 minus p, we get 10.5. Barely squeak by, but we have 10 or more. So we meet large counts for population 1 for our seniors. What about for the juniors? What happens when you do n times p there? 12.6, which is bigger than 10, so we're good. And n times 1 minus p? 17.4, which is more than 10. So we get approximate normality here. What is the mean for the difference? What is the mean for the difference of p hat s minus p hat j? 0.23. And before we can find the standard deviation, what do we have to pause and do? 10%. Have to check 10%. This is why they gave you the total number in the class for seniors and for juniors. We use the 30 as our sample for n times p, but we need the entire population so that we can check our 10% condition. What's the maximum number of seniors we could sample? There are 315. What's the maximum number of seniors we could sample and still meet our 10% condition? 31.5. Are we sampling more than that? No, so we're good there. What's the maximum number of juniors we could sample and still meet our 10% condition? 38.9. So we are less than 10% on both of those. So then we can go in and we can calculate our standard deviation. So we do probability of senior, not probability of senior, but probability for the seniors times 1 minus the probability for the seniors over the sample size of seniors, plus probability for our juniors times 1 minus the probability for the juniors over the sample size of the juniors. So both of these are going to be over what? Over 30, because our samples were 30 for both of them. And what do you get? Mm-hmm. 0.125 or 0.1253, depending on where you round it at. If you had 0.125, that is perfectly fine. So number 3, what is the probability that the difference in sampling proportions, senior minus junior, of students with parking passes is greater than 30%? How did we say this was distributed? Normally. So you're going to start with your picture. And we have our mean right here, 0.23. We have our standard deviation, 0.1253. What else needs to go on the picture? 0.30. And then shading which way? Shading to the right, 30% or greater. So your picture should look something like this. So the probability of p hat senior minus p hat junior being greater than or equal to 30%. We're going to do our normal CDF. Lower bound of 0.30, upper bound of stupid large. Mean of 0.23, standard deviation of 0.1253. Yes? So that's a great question, and you're right. I probably shouldn't have put the or equal to on here. However, when we're talking about a normal CDF, there is no difference in the probability between when it has the or equal to and when it doesn't. So that's why I'll sometimes forget and put the or equal to even though it doesn't say it. That's not true for binomial, but it is true for normal. What do we get? Yep. 0.2881, 0.2882, depending on exactly how you round. If you wrote 0.288, that'd be perfectly fine. We're going to do just a little bit. So if you want to flip over to page 17 for me. There's some information on page 16. Actually, why don't you have your notes so you can see 16 and 17 at the same time? Hold the notes out so you can see pages 16 and 17 at the same time. So on page 16, you have the heights for all the power forwards in the NBA. I don't remember what year I pulled this data, so I apologize. It's a little dated. But we had pulled the heights for all of the power forwards in the NBA. How tall do you need to be to play in the NBA? Well, depends on the position you want to play. We're going to try to find the average height of all the power forwards by taking a random sample of 5 power forwards. What's the population? All the power forwards anywhere ever? In the NBA. All the power forwards in the NBA. What's the sample? 5. 5 what? 5 power forwards in the NBA. Specifically, whichever ones we end up selecting, right? The sample is the 5 selected power forwards in the NBA. If you look at page 16, like I said, that has all the heights for the power forwards in the NBA in, I don't remember what year. But if you look down at the bottom, underneath that list of all of their heights, there's a dot plot down there, and there's some summary statistics. I want you to look at the dot plot. That's the population distribution. What is the shape for the population distribution? I would say it's approximately normal just looking at it. If you look at the summary statistics, you can find the mean. What is the mean for the heights of all the power forwards? 80.087. Is that a sample mean or is that the population mean? That's the population mean, so that's mu. That's not x bar, that's mu. What's the standard deviation? 1.519. Is that population standard deviation or sample standard deviation? Population. So what do we use to represent the population standard deviation? Sigma. What we're going to do right at the beginning of class tomorrow is you guys are going to select your random samples. You're going to do this 3 times total. So I'm going to show you the next page, but this is where we're going to start class. You're going to use a graphing calculator to select a random sample of 5 random numbers between 1 and what? 115, because there were 115 power forwards on the list. So you're going to choose 5 random numbers. You will use those to then go find them on the list, find their heights. You're going to write their heights down here on this line. And then you're going to calculate the average. And you'll do that 3 times over. And then we'll make a dot plot from that. That's first thing we're going to do tomorrow, okay? Very first thing we're going to do tomorrow is what? Grade homework. Then we will select our samples.